Now go to the derivation of the kinetic energy, half mv squared. We assume a smooth surface, and then we have a box where a net external force acts on the box over a distance. The object will accelerate, or that is, it will gain speed or kinetic energy. The work done by the force will become the kinetic energy of the object. Work done by the force F is force times distance, or move in the direction of the force. Okay. Force is by Newton's second law is ma, so the work done by the force F is equals to max. If you recall your kinematics formula, using v squared equals to u squared plus 2ax, where x is the displacement, we can rearrange the equation such that ax equals to half v squared minus u squared. Substituting the ax into the work done equation, we will have work done by F is equal to half mv squared minus half mvu squared. For simplicity, we can consider the object to be initially at rest. Therefore, the work done is equals to the kinetic energy gain equals to half mv squared. So in more general terms, the work done by a force F is equal to the change in the kinetic energy. Example 5. During takeoff, an aeroplane's speed changes from 0 to 400 meters per second while traveling 1000 meters along a horizontal runway. If its mass is 2 times 10 to the power of 4 kg, find the minimum driving force which needs to be applied to it. Assume that friction and air resistance are negligible. Okay. Think about what is the significance of the horizontal runway. The solution, let F be the minimum driving force which is exerted by the engine of the plane. So the work done by the net force on the plane, in this case is just the force exerted by the engine, is equals to the gain in the kinetic energy of the plane. I said the net force is just F because air resistance friction is negligible. Formula for work done is Fs cosine theta. Since F and the displacement is in the same direction, theta is 0, so Fs is equals to the gain in the kinetic energy. Also, you are told that the aeroplane starts from rest, so the initial kinetic energy is 0. So Fs is equal just to the half mv squared. Substituting in all the quantities that are given in the question, you can solve for F is equal to 1.6 times 10 to the power of 6 newtons. Next, we proceed to the derivation of the gravitational potential energy, which you all know is mgh. We consider the mass m, okay, being raised to a vertical height of h by an external force F, and this is to be done, or the mass is to be raised at a constant speed, okay, to the maximum height. So when we say that it is been move at constant speed, then we can rule out any change in the KE. Also, since it is moving at constant speed, there is no net force on the mass m. So net force is equal to 0. So in this case, the external force F applied to raise the object up is equal to the weight of the mass. The work done by the force F is equals to the force, the product of the force and the displacement. So in this case, it's just mg, which is the force multiplied by h, displacement. Therefore, the gravitational potential energy is equals to mgh, where h is the vertical height above a reference level, and we define the gravitational potential energy is 0 at the reference level. What are some things to note in the derivation? Just as in the case of the work done producing motion in an object, in the previous section, work done equals to the change in kinetic energy. mgh here refers to the change in the gravitational potential energy, not the absolute value of GPE. In chapter 7 on gravitation, you will learn that the absolute value of GPE is always negative. 2. The gravitational acceleration g is assumed to be constant. The rule of thumb for this assumption is that the height h is less than 1 km. In chapter 7, again on Newton's law of gravitation, you will learn that the magnitude of g depends on the distance away from the Earth's center. The change in GPE is dependent on only the change in vertical height, regardless of the path taken. Some food for thought. What happens if the external force F applied is greater than mg? So in such a case, the work done by the external agent will result not just an increase in GPE, but in an KE as well. We now combine all the concepts that we have learned earlier on to solve some examples. Okay, we look at work example 6. We consider one of the tallest and the fastest roller coasters in the world is the Steel Dragon in Mie, Japan. The ride includes a vertical drop of 93.5 meters. The coaster has a speed of 3 meters per second at the top of the drop. If we neglect friction, calculate the speed of the riders at the bottom. And part B, taking friction into consideration, and that the actual speed of the riders at the bottom is 41 meters per second, determine the work done by friction on a 55 kilogram rider during the descent of 93.5 meters. It is always good to, in the solution, to draw a sketch of the situation here. So here we have the maximum height of the roller coaster is at 93.5 meters, and at the base of the, and here is the base of the roller coaster, okay, which we will set as the reference level of 0 gravitational potential energy. first method we can use to solve this problem is the approach called the loss in energy equals to the gain in energy. This method would have been the method you use in your O levels. So by the principle of conservation of energy, since no energy is lost, okay, lost from the system, whatever is lost in GPE by the coaster at the initial part, at the initial will be equals to the gain in kinetic energy at the final position. So when the coaster descends from its maximum height to the base of the roller coaster, it loses the GPE of mgh. And at the same time, it gains in KE, which is given by the equation half mv squared minus half mu squared, which you have seen in the derivation of kinetic energy. Substituting in the values for the mg, the m will cancel off, the m will cancel off, leaving the g and the h and the u square. From solving the equation, you will obtain the speed of the riders at the bottom, v, to be 42.9 meters per second. Now we do a second approach to solving the this question. The second method is called the total energy approach. The total energy initial, which is at the top, okay, will be equals to the total energy at the bottom of the roller coaster. So again, the principle of conservation of energy is still the same principle that we work on. So since there's no work done by any external forces, work done actually is zero, since there is no friction or no applied force on the roller coaster. So the final energy at the bottom equals to the initial energy at the top. The final energy at the bottom here is made up of the kinetic energy at the final position as well as the GPE at the final position. And this is equal to the KE at initial and GPE at initial position. We mentioned earlier that we have to set a reference level. So at the reference level at the base of the coaster, the gravitational potential energy is zero. Okay, so at the top, the initial kinetic energy is zero. So we will have mgh equals to half mv squared. Again, the m can be cancelled, and that will lead you to the same equation as you have in the method 1. Okay, let's look at now in the case for part B where there is a friction. Okay, again we use method 1 where the loss is equals to the gain. Okay, whenever you have friction, then the loss in the gravitational potential energy here will be equals to the gain in the kinetic energy plus some work done by the friction. So substituting in the appropriate formula, gravitational potential energy is mg delta h, and the gain in kinetic energy is the final kinetic energy minus the initial kinetic energy, and then plus the work done by friction. Substituting in the values, you can work out the work done by friction is equals to 4470 joules to three significant figures. Again, method 2. Using method 2, using the conservation of energy and the work energy relationship where work done is equals to the change in energy. Work done by friction equals to the energy at the bottom minus the work done of initial, which is at the top. Work done by friction is negative, so we put a negative work done, a negative work done F, okay, by friction. This is equals to the kinetic energy at the final plus the kinetic gravitational potential at the final position. Subtract against the initial KE plus the initial gravitational potential energy. If you rearrange the equation and substituting in the values, you will have half mu squared plus mgh equals to half mv squared plus 0, where the 0 is the reference level gravitational potential energy plus the work done by friction. So again, if you substitute in the values, you will have work done by friction equals to 4470 joules. Let's look at work example 7. There's a 80 kg baseball player and he slides to a halt from a speed of 8 meters per second in a distance of 4 meters. What is the average horizontal frictional force exerted on him by the ground? Is the work done by the frictional force on the man positive or negative? Okay, again, we have a simple diagram to illustrate the situation. Since the man is sliding towards the left, friction will be exerted on him will be towards the right direction. So the solution, if we let F be the average horizontal frictional force, and then we apply the principle of conservation of energy on the man, work done by friction is equals to the change in the energy of the man from final to final minus the initial. Work done by friction is a negative, okay, equals to the final KE minus the initial KE. Recalling that we mentioned that the change in energy is always the final minus the initial. Okay, there is no GPE here because all the action takes place at the ground level or at the same level. So work done by friction is equals to force of the friction multiplied by the displacement. Okay, is equals to 0 minus half mu squared. Final KE is 0. Substituting in the appropriate values, you will obtain a frictional force of 640 newtons. As to the question whether it is positive or negative work, frictional forces is always does negative work because the force and the displacement S is in opposite direction. Let's look at another example. Example 8. You have a crate initially at rest. It's been pushed 10 meters along a horizontal surface by a horizontal force of 80 newtons. The frictional force opposing the motion is 60 newtons. How much of the work done is converted into thermal energy and how much into KE of the crate? If you draw a free body diagram to illustrate the problem, forces indicated on the crate will include the force exerted by the external force exerted on the crate, which is 80 newtons, or we call it FA here. And the frictional force that is opposing the motion here is F subscript F, 60 newtons. Of course, thermal energy generated will be the work done by frictional force. So in this case, it's just Fs cosine theta. Since the displacement 10 meters is to the right, which is opposite in direction to the frictional force, the angle is 180 degrees. The displacement is 10 meters. The force is 60 newtons. So the thermal energy generated is 600 joules. Okay, you apply the principle of conservation of energy to this situation here. So the work done by the external agent, okay, will be equal to the change in the kinetic energy plus the work done to overcome friction. So substituting in the numbers again, work done by the external agent or external force is 80 times 10 equals to the gain in KE plus the 60 times 10, which is the work done by friction. So the gain in KE equals to 200 joules. Example 9. A 3.2 kg trolley, initially moving at 5 meters per second at a height of 4 meters, encounters a hill of 5 meters as shown in the figure. At a later point, there is a horizontal spring at a height of 2 meters. Show using numerical calculations whether the trolley reaches the spring, and if so, calculate the maximum compression of the spring. Okay, to solve this problem, we have to check whether the trolley, if it were to reach the spring, it has to first overcome the hill. This can be validated by calculating the KE at the top of the hill. If the KE is greater than 0, then the trolley has sufficient energy to move beyond the hill towards the spring. The energy required to reach the top of the hill is equal to the GPE that is required. That is related to the height difference between the point A and the top of the hill, which is equal to 31.4 joules. KE possessed by the trolley at start point is calculated to be 40 joules. So since the KE is greater than the GPE required to reach the hilltop, the trolley will be able to overcome the hill to get to the other side. We use the approach of the loss in energy equals to the gain in energy to find the compression of the spring. At point A, the trolley has kinetic energy and gravitational potential energy. At point B, when the spring experiences maximum compression, it has only elastic potential energy. Therefore, the loss in KE plus the loss in GPE of the trolley will be equal to the gain in the elastic potential energy of the spring at point B. The loss in KE is equal to the final KE minus the initial KE, and the loss in GPE is equal to the difference in height of the point A and point B. This is equal to the half kx squared, where x is the maximum compression of the spring. Solving the equation, you get a value of x equals to 1.31. Let's look at the alternative approach to solving this problem using the principle of conservation of energy on the trolley and using the work energy equation. Work energy equation, work done is equal to the change in the energy. Since work done equals to 0 because there are no external forces and also there's no work done on the system, therefore the initial energy at the start point will be also equal to the energy at the top of the hill. We set the GPE to be equal to 0 at the ground level. In this way, the initial energy making up of the KE and the GPE is given as follows here, and the final KE which we want to determine plus the final GPE, which is the GPE at the top of the hill here, we can determine that the final KE will be 8.61 at the top of the hill. Since the final KE is greater than 0, the trolley must have sufficient energy to overcome the hill to reach the other side. Next, to find the maximum compression of the spring after the trolley has overcome the hilltop. Again, we apply the principle of conservation of energy. Work done is equal to change in energy. And again, since there is no external forces on the system, there's no work done on the system, so the initial energy at the point A will be equal to the final energy at the point B. Initial energy at point A consists of the KE and the GPE and 0 elastic potential energy. The final energy at point B consists of 0 KE since the trolley comes to a stop, and GPE since the spring is still at a certain height from the ground level, and half kx squared. Solving the equation gives you 1.31, which is the same answer as previous. So as you see, solving principle of conservation of energy problems, we suggest a series of steps that you should do. The first step is to draw a picture of the situation, which will help you to visualize the situation much better. Second step, set up the system, okay, the system for which you will apply the principle of conservation of energy. Next step is to choose the final and the initial positions where you will apply the before and after of the system. If the body changes its height in the situation, then you would want to choose a reference level where the GPE is 0. Okay, how you would do that is to normally you will choose the lowest point of the system. Okay, if springs are involved, choose the unstretched spring position to be the position of 0 extension. If there is no external force or friction, then work done is 0, meaning that the sum of the initial energy, which is made up of PE and kinetic energy, will be equals to the final energy of making up of the PE and the kinetic energy.